Electric current. Most researchers agree that an electric current is simply the movement of an atomic negative charges electrons around a circuit. The simplest of all circuits could be the length of copper wire that contains lots of atoms that each has a plentiful supply of electrons. Although in practice, to prevent the copper wire from short circuiting the supply voltage, circuits always also contain other components like light bulbs, fans, or heaters, etc. The electrons move around the circuit when dislodged from the atoms in the copper by an electric force, a voltage, for example, from a battery. The battery sucks in electrons at one end and pushes them out at the other end. Electric currents are known to be associated with various effects. For example, whenever an electric current flows through a wire, the wire gets hot. The heat effect is thought to be caused by a collision between the moving electrons and the stationary atoms inside the wires. In 1831, Michael Faraday, using a simple compass, was the first to show that a flow of electric current through a wire produces a magnetic field that encircles the wire. Figure 11b. No orthodox researcher understands why moving electrons produce a magnetic field or why the field encircles the wire as it does 90 degrees from the direction of the current flow. To distinguish this kind of magnetism from that of a permanent magnet, Faraday termed the effect electromagnetism so that observers would know that it is only produced when an electric current flows. Later experiments revealed that when a piece of copper wire is wrapped around a pencil into the shape of a coil, the magnetic field intensifies greatly and the direction of the magnetic field shifts by 90 degrees to follow the direction of the current flow. He called his coil an inductor because when a permanent magnet is swiped across the coil, figure 12a, in a current that does not contain a battery, the electric voltage is mysteriously inductively produced into the coil, which then forces an electric current to flow momentarily, a pulse of current that dies away very quickly around the circuit. This technique is widely used today. When a credit card is swiped across a card reader, magnetic information previously encoded into a magnetic strip causes a short-lived electrical current to flow that are then decoded by the computer. Faraday also discovered that the amount of induced voltage depends on which way around the coil is in relation to the cutting magnetic field. More voltage is induced into the coil when the cutting magnetic field is vertical to the coil, figure 12a, and much less, virtually none, when the cutting magnet is horizontal to the coil, figure 12b. He was the first to discover that the amount of induced voltage across a coil is proportional to the number of coil links cut by the magnetic field, figure 12c. In summary, Faraday's greatest contribution showed that when an electric voltage is applied to a circuit, it forces an electric current to flow in the circuit, and the flow of the current produces a magnetic field. And he showed that when a magnetic field is swiped across a coil, it produces a voltage in the coil that the induced voltage then behaves like a battery that momentarily forces a current around the circuit, or put another way, a voltage can produce a magnetic field and a magnetic field can produce a voltage. The two are 90 degrees apart, but no one knows why.